First of all, and before starting our presentation, we would like to thank the organization committee of this 9th International Renewable and Sustainable Energy Conference. In this presentation, we are going to introduce the Cascade H-Bridge Multilevel Inverter for wind energy conversion system application. Right? Let's make a start. The session has been drawn to 4 points in particular, which we'd like to outline to you briefly. So we're gonna start with background purposes, then we're gonna move to description and modeling of the wind energy conversion system. After that, we're gonna move to the overview and model of the H-Bridge 5-level inverter, and finally we're gonna present results, discuss them, and keep some perspective. According to the Global Wind Energy Council statistics, they expect that over 469 gigawatts of new capacity will be added in the next 4 years. There is nearly 94 gigawatts of new installation each year until 2025. Things that lead the researchers to carry out investigation and amelioration in order to contribute in this. To ameliorate the wind energy conversion system, there are many points to improve. One of them is to satisfy a standard IEEE condition, which include limitation of GHG factor and current harmonic, and this point is the one that takes our interest for this work. Now we're gonna move to a description and modeling of the wind energy conversion system, which is a structure that transforms the kinetic energy of the incoming air into electrical energy. This conversion takes place in 2 steps. The first one is the wind turbine, which is composed of 3 blade rotor and gearbox. This first part transforms the wind power into mechanical one, that is converted into electrical one using a double feed induction generator. In order to inject the power generated into the grid, we are using inverter to adapt the electrical power to grid system services and IEEE conditions. Now we're gonna move to the modeling of the wind energy conversion system. We start with the wind turbine. So we modeled the aerodynamic part using the mechanical power. And in order to extract the maximum power possible from the wind, we are using the maximum power point tracking algorithm that we modeled as shown in the article. After that, we move to the model of the wind turbine, which is composed of gearbox and drive shaft. We modeled them using the equation as shown. This figure presents the whole model of the wind turbine plus the MPPT control. Now we have the mechanical power. We converted it into an electrical one using the double feed induction generator that we modeled in the park model using the equation as shown. To finally get the whole model present in the figure. To ensure that the active and reactive power of the double feed induction generator follow the reference, we model the PI controller as shown in the loop. To inject electrical power produced to the grid, we must respect grid's condition and parameter. That's why we're using inverter. And in order to have better performance, for our case, we choose to use Multilevel Inverter. Now we're gonna move to the model of the Multilevel Inverter. For this work, we are using an H-Bridge 5-level inverter for the many advantages they have in terms of GHG factor reduction. We start our modeling using the electrical model of an H-Bridge 5-level inverter single phase as shown. So the 5-level output waveform is obtained by respecting the following switching state of the used semiconductor. And by using 3 of the previous model, we obtained the model of the H-Bridge 5-level inverter. Now we're gonna move to the results of simulation. So we start by a separate simulation of 2-level and 5-level inverter. And according to the FFT analysis, we can conclude that the 5-level inverter improved the resolution in the voltage harmonic content. Using a 2-level inverter gives us a GHG that is equal to 68%, and the use of the 5-level inverter gives us a GHG that is equal to 24%, as shown in the figure, which means that our inverter reduced GHG by about 44%. We're gonna move to the simulation of the whole wind energy conversion system using a 5-level inverter. The first figure presents the wind profile used. The second one shows that the CP follows its CP max. The third one presents the electrical mechanical torque, and the fourth one presents the produced power. And finally, we did a comparative analysis of output voltage provided by the wind energy conversion system using 2-level and 5-level inverter. So according to the FFT analysis, we can conclude that the THG factor was being reduced by about 66%. To conclude, the use of 5-level inverter presents reduction of THG of the output voltage, the amelioration of the output waveform quality enabled to reduce output filter, and the block-in voltage of the 5-level switches is reduced so that the cost of switches. And in perspective, we are thinking to apply a higher level inverter and see the amelioration of THG factor, and to study the participation of the wind energy conversion system in the system service of the grid. Thank you for your attention.